The illusion of a crowded sky. On a clear night, far from city lights, the sky looks full. Stars crowd the darkness in every direction, some faint, some blazing, some clustered into rivers of light so dense they blur together. It's easy to look up and feel surrounded, to feel that the universe is a busy, populated place, teeming with activity at every scale. That impression is one of the most profound illusions in all of science. The night sky you can see from Earth contains roughly 5,000 to 10,000 stars, visible to the naked eye. Those stars occupy an enormous volume of space, scattered across hundreds of light years in every direction, separated by distances so vast that no human technology has ever come close to crossing them. The stars that look close together from our vantage point are almost never actually near each other. They just happen to lie along the same line of sight from a single planet in a single solar system on one edge of one galaxy. When you pull back and look at the actual structure of the cosmos, not what it looks like from Earth, but what it actually is at every scale, what you find is not fullness. It is not abundance. What you find is emptiness, almost beyond the capacity of human intuition to hold. The universe at its core is made of almost nothing. Most of the space between stars is a near-perfect vacuum, colder and emptier than any chamber ever constructed in a laboratory on Earth. Most of the space between galaxies is more extreme still. And most of the volume of the observable universe, the vast majority of all the space that exists, as far as we can measure, is occupied by enormous regions so devoid of matter that a single hydrogen atom per cubic meter would count as crowded. What makes this more than a curiosity is the reason for it. Because the emptiness isn't random. It isn't left over from some early chaotic state that just hasn't had time to fill in. The emptiness is there because of a specific process that has been running since the very beginning of time, driven by a force that currently dominates the universe and is accelerating. The voids are not a gap in the story. They are, in a very real sense, the story. And when you understand what's happening inside them, and what they are doing to everything else, the picture that emerges is unsettling in a way that is difficult to shake. What we mean by empty, before we can talk about how empty the universe is, it helps to be precise about what empty actually means at different scales, because the emptiness is layered, and each layer is more extreme than the last. Start close to home. The space between Earth and the Moon is, from a human perspective, incomprehensibly vast. About 384,000 kilometers, a distance that would take years to walk. But from a cosmic standpoint, it's nothing. It's a corridor. The space between Earth and the Moon contains trace amounts of solar wind particles, stray hydrogen atoms, and interplanetary dust, which is not much, but it is something. Move outward to the space between the Sun and its nearest stellar neighbor, Proxima Centauri, which lies about 4.2 light-years away. This gap, more than 40 trillion kilometers of it, is effectively a void. The density of matter in interstellar space runs to roughly 1 atom per cubic centimeter, which sounds like very little because it is very little. The best vacuum chambers humans have ever built, using decades of precision engineering, can achieve particle densities in the same ballpark. The space between stars is essentially the best vacuum achievable, and it stretches for light years in every direction. Now, step back further to the scale of entire galaxies. The Milky Way is a disk about 100,000 light-years across and contains somewhere between 200 and 400 billion stars. But those stars do not fill the disk. The average distance between stars in our galaxy is several light years, meaning the stars, enormous as they are, occupy only a tiny fraction of the total volume. If you shrank the Sun to the size of a grain of sand, the nearest other star would be about 4 kilometers away. That gives some sense of how much nothing lies between them. And then consider the space between galaxies themselves. The Milky Way is part of a small cluster of galaxies called the Local Group, which spans a couple of million light years. Beyond that, the nearest large galaxy cluster is tens of millions of light years away. The intergalactic medium, which are the gas and particles drifting through the space between galaxies, has a density of roughly 1 particle per cubic meter, or less. In interstellar space, you get about 1 particle per cubic centimeter. In intergalactic space, you get 1 per cubic meter. Intergalactic space is roughly 1,000,000 times emptier than the space between stars. If you could somehow swim through the deepest intergalactic voids, you might encounter a single hydrogen atom in a volume equivalent to an entire football field of space. In some regions, the number is even lower than that. These places do not have names or star systems or any landmark by which you could orient yourself. They are regions where the concept of locality barely applies, where the nearest matter in any direction might be millions of light years away, and the nearest star might never be reached regardless of how long you travel. This is the universe. Not the one visible from a mountaintop on a clear night, but the actual one, mapped by decades of astronomy, by redshift surveys and galaxy catalogs, and the mathematics of cosmology. It is a universe where matter is vanishingly rare, and the gaps between everything are vast enough to make the mind go quiet just trying to imagine them. The numbers, when you actually sit with them, become almost impossible to hold. The observable universe is roughly 93 billion light-years in diameter. It contains somewhere on the order of 2 trillion galaxies, a number revised sharply upward from earlier estimates once deeper telescope surveys became available. Each of those galaxies contains anywhere from hundreds of millions to hundreds of trillions of stars. The raw count of stars in the observable universe is conventionally estimated at around 200 billion trillion, a 2 followed by 23 zeros. This is a staggering figure by any human standard. And yet, the total volume of the observable universe is approximately 4 times 10 to the power of 80 cubic meters. The total volume occupied by all stars combined, all of them across all 2 trillion galaxies, is roughly 10 to the power of 57 cubic meters. The ratio of stellar volume to total cosmic volume is somewhere around 10 to the negative 24, meaning that stars, for all their number, occupy about 1 part in a trillion of the observable universe's volume. Everything that burns, everything that shines, everything that has ever been the source of light in the cosmos, fits into a fraction of total space so small that if you tried to represent it on a diagram drawn to scale, the stars would be invisible, not just tiny, but genuinely invisible, smaller than any pixel any display could show. The universe is not slightly empty, in the way that air is mostly empty space between atoms. It is cosmically, overwhelmingly, structurally empty, at a scale that dwarfs every other property of it. The matter, the light, the drama of astrophysics, all of it happens in a fraction of the available volume so small that from the universe's perspective, matter might as well be a rounding error. The web and the void. At the largest scales that astronomers can map, which is hundreds of millions of light years across, the universe has a specific structure. It is not a uniform fog of matter spread evenly through space, and it is not a random scatter of galaxies strewn about without pattern. It has a form, one of the most remarkable forms in all of nature. The structure is called the cosmic web. It got that name because when you map the distribution of galaxies across enormous volumes of space and step back far enough to see the whole picture, what you find looks remarkably like a web, or a foam, or the branching of a neural network viewed from outside. Galaxies cluster along long filaments, dense strands tens of millions of light years in length, that thread through space in every direction. Where filaments intersect, enormous concentrations of matter accumulate into galaxy clusters and superclusters, dense nodes of gravitational activity containing hundreds or thousands of galaxies. Between those nodes, the filaments stretch outward like bridges, connecting the dense regions across the emptiness. The discovery of the cosmic web was gradual, assembled over decades as the tools for mapping galaxy positions became precise enough to reveal the structure. Early redshift surveys in the 1970s and 1980s, particularly the work by Valérie de Lapparent, Margaret Geller, and John Huchra at the Harvard-Smithsonian Center for Astrophysics, produced the first slice of the universe maps that made the pattern visible. Their 1986 survey revealed that galaxies were not distributed randomly, but were arranged on the surfaces of large bubble-like structures with vast empty regions inside, the first clear observational evidence of the voids and the web simultaneously. It was described at the time as looking like a slice through a foam or a sponge, and the image was startling enough that it changed how cosmologists thought about the large-scale structure of the cosmos. Subsequent surveys became progressively larger and more comprehensive. The 2DF Galaxy Redshift Survey mapped over 200,000 galaxies in the late 1990s and early 2000s. The Sloan Digital Sky Survey, which began collecting data in 2000 and is still ongoing in various forms, eventually mapped over 3 million galaxies in 3 dimensions. These surveys confirmed and refined the picture. Galaxies are concentrated in a complex web of filaments, walls, and clusters, separated by enormous voids. The Sloan Great Wall, identified in 2003, is a structure of galaxies more than 1 billion light-years long. The kind of feature that only becomes visible when you have enough data to see the web at the scale at which it was built. The numbers that emerge from these maps are genuinely striking. The filaments of the cosmic web are typically tens of millions of light-years thick and can stretch for hundreds of millions of light-years in length. The superclusters at their intersections can span hundreds of millions of light-years in diameter and contain thousands of galaxies. Our own Milky Way is part of a supercluster called Laniakea, identified in 2014 using galaxy velocity measurements, which spans roughly 520 million light-years and contains approximately 100,000 galaxies. Laniakea itself sits on the edge of a much larger structure, and between these filaments, between the walls and sheets and nodes of galaxies, are the voids. Vast, roughly spherical regions of space that are almost completely empty of matter. The smallest cosmic voids are about 20 million light-years across. The largest can stretch for hundreds of millions of light-years. They account for roughly 80% of the total volume of the observable universe. The cosmic web, all those spectacular filaments and clusters and walls that astronomers photograph and celebrate, occupies the remaining 20% of the volume and contains essentially all of the matter. What this means is that the structure we tend to think of as the universe, the galaxies, the clusters, the grand architecture of the web, is, volumetrically speaking, a thin skin stretched over an enormous amount of nothing. If you picked a random point in the observable universe, there is roughly an 80% chance you would land in a void, in a region where no galaxy is nearby, where the nearest star is hundreds of millions of light years away, where there is almost nothing around you in any direction for as far as can be measured. We don't tend to visualize the cosmos this way because we observe it from inside a galaxy. And galaxies are embedded in the filaments of the web, in the denser regions where matter has collected. Our view of the universe is therefore systematically biased toward the populated parts. It would be like trying to understand what a forest looks like by only ever standing among the trees. The voids, by contrast, are regions that light from distant galaxies simply passes through. They leave their mark on our observations in subtle ways, but they offer no landmarks, no structures, no sources of light to anchor the eye. They are places where the act of looking turns up nothing, and where for a long time, astronomers had little reason to look at all. That changed when scientists started asking a different kind of question. Not what is in the voids, but why the voids exist in the first place. The answer turned out to be far more consequential than anyone expected. Seeds of emptiness. The universe was not always structured this way. There was a time early in cosmic history when the voids did not exist, when the universe was so young and matter was so evenly distributed that the concept of a void would not have had any meaning. That time was the first moments after the Big Bang, roughly 13.8 billion years ago. In those early instants, the universe was hot, dense, and almost perfectly uniform. Almost, but not quite. The matter and energy packed into the early universe were not spread out in exact uniformity. There were tiny density variations, fluctuations on a scale so small they were quantum in nature. In some regions, the density of matter was very slightly above average. In others, it was very slightly below average. The differences were minuscule, on the order of 1 part in 100,000. But those differences were real, and they were going to matter enormously. We can actually see these fluctuations, the cosmic microwave background, the faint glow of thermal radiation left over from when the universe was about 380,000 years old and first became transparent to light, is essentially a photograph of those early density variations, imprinted on the sky in the form of tiny temperature differences. When the Planck satellite mapped the CMB with precision across the entire sky, it resolved these variations in extraordinary detail, a patchwork of very slightly warmer and cooler spots, each corresponding to a region that was very slightly more or less dense than average, embedded in a universe that was otherwise almost perfectly smooth. These fluctuations were the seeds of everything that followed. Gravity, patient and relentless, began to amplify them. In regions that were slightly denser than average, the extra mass exerted slightly more gravitational pull. That pull drew in matter from the surrounding space, increasing the local density further, which increased the gravitational pull again, which drew in more matter still. This self-reinforcing process, operating over billions of years, is how the filaments and clusters of the cosmic web grew out of what were once barely perceptible ripples in a smooth distribution of gas. But matter cannot flow into dense regions without flowing out of somewhere. As gravity pulled matter toward the slightly overdense areas, it drained matter away from the slightly underdense ones. Regions that started out slightly emptier than average lost matter to their denser neighbors, becoming emptier still. Over time, those regions grew increasingly hollow. The filaments built themselves up by hollowing out the space between them. The walls of galaxies constructed themselves from material that was swept out of the volumes they now surround. The great structure of the cosmic web and the great emptiness of the voids are not two separate phenomena. They are the same phenomenon, viewed from two different perspectives. This is a subtle but important point. The voids were not left behind by some process that failed to populate them. They were actively created by the same gravitational dynamics that built the web. Structure and emptiness co-produced each other, carved from the same initial material by the same long, slow action of gravity, working on tiny inherited inequalities. And because the initial fluctuations were set by quantum processes during a period called inflation, a period of extremely rapid expansion in the first tiny fraction of a second of cosmic history, the structure of the web and the existence of the voids ultimately traces back to the quantum level. The largest empty regions in the observable universe, some of them hundreds of millions of light years across, exist because of events that happened on subatomic scales in the first 10 to the power of negative 32 seconds. That is perhaps the most extreme case of small causes producing large effects in all of natural history. The Boötes void. In 1981, an astronomer named Robert Kirshner at the University of Michigan was working on what seemed like a straightforward cataloging project. He and his team were measuring the redshifts of galaxies, the degree to which their light had been stretched toward the red end of the spectrum by the expansion of space, and using those measurements to map the three-dimensional distribution of galaxies in a portion of the sky. Redshift serves as a proxy for distance. The more a galaxy's light has been stretched by cosmic expansion, the farther away it is. By measuring redshifts across a large sample of galaxies, you can build up a three-dimensional picture of how they are distributed in space, a technique that was still relatively new in the early 1980s and was producing results that regularly surprised their authors. Kirshner's map, as it filled in, revealed something that had no good precedent in the existing literature. In the direction of the constellation Boötes, at a distance of around 700 million light-years from Earth, there was a region of space where essentially no galaxies existed at all. Not fewer than expected, nearly none. A roughly spherical volume approximately 330 million light-years across contained, at most, a handful of galaxies, where statistical expectation predicted thousands. The region had no structure, no filaments, no clusters, no signs of the ordinary density variations that characterized the rest of the survey. It was, by the standards of the cosmos, extraordinarily empty. Kirshner and his colleagues reported the finding cautiously, as scientists tend to do when confronted with results that seem to exceed the bounds of what their theories predict. But subsequent surveys confirmed it. Follow-up observations with increasingly sensitive instruments found a total of about 60 galaxies within the Boötes void, a number so far below what a region that size should contain that the structure earned the nickname the Great Nothing, or sometimes simply the Great Void. A region that size in a typical part of the universe should contain something on the order of 2,000 galaxies. What Kirshner's team found was approximately 60, arranged in a loose tube-shaped chain running through the middle of the void, as if clinging together in an otherwise barren landscape. Astronomer Greg Aldering, who later studied the Boötes void extensively, made a striking observation about the scale of this emptiness. If the Milky Way had been located at the center of the Boötes void, rather than in its actual position along a filament of the cosmic web, our astronomers would not have discovered the existence of galaxies beyond our own until sometime in the 1960s, at the very earliest. The nearest galaxies in any direction would have been so far away, on the far walls of the void, that they would have been beyond the reach of early telescopes. The universe would have appeared to early 20th century observers to consist of nothing but the Milky Way and empty space, a cosmos of one galaxy, surrounded by darkness. That thought experiment does something important. It shows how deeply our view of the cosmos depends on where we happen to be sitting inside it. We know the universe is full of galaxies, not because their presence is obvious, but because we're close enough to the nearest ones to detect them. In a different location, the picture would have looked very different and very much emptier. The Boötes void is almost certainly the result of smaller voids merging over time, a process that cosmologists believe happens throughout the universe as dark matter and gravity continue to amplify the contrast between dense and empty regions. Smaller voids coalesce the same way soap bubbles do when they touch. The wall between them dissolves, and they merge into a larger bubble. The tube of galaxies running through the interior of the Boötes void is likely a remnant of those original walls, matter that was caught between merging voids and not yet swept out to the edges. What the team found when they began following up on those 60 galaxies in detail was equally unusual. Unlike typical void-edge galaxies, which tend to be elliptical in shape, similar to old stellar systems that have long since stopped forming new stars, most of the galaxies scattered through the Boötes void are spirals. Spiral galaxies tend to be rich in gas and ongoing star formation, which suggests these solitary objects have access to gas they are still processing, still building from. They may have been slower to evolve precisely because they have spent their existence far from the gravitational stirring of dense clusters, undisturbed by the collisions and interactions that shape galaxies in more crowded environments. They are different kinds of galaxies than their counterparts in the web, shaped by the particular silence of the place they inhabit. One of these galaxies, stranded deep in the interior of the void, has attracted informal attention simply because of its situation. Astronomers studying the distribution of galaxies in the Boötes void have noted a single spiral galaxy located deep in its interior, not at the edge or in the tube of galaxies that threads across the middle, but truly deep inside the void, far from any other major structure. It has been described as the loneliest galaxy in the known universe, a spiral with ongoing star formation, producing light that has to travel hundreds of millions of light years before it encounters any other significant concentration of matter. Around it, in every direction, there is essentially nothing. No cluster, no filament, no neighboring galaxy large enough to be visible to any observer that might hypothetically exist within it at unaided eye range. The Boötes void was for a long time treated mainly as a curiosity, a remarkable outlier, a record setter, but not necessarily something with deep implications for the overall picture of the cosmos. That view began to shift when astronomers started taking the voids more seriously as a class of object, and when the measurements started to reveal what was happening inside them. What's actually in a void? For a long time, the interest in cosmic voids was limited by a simple problem. There was not a lot you could obviously study inside them. Voids are defined by the absence of galaxies, which means they are also, for the most part, absent the stars, gas clouds, and other structures that astronomers typically use as probes of the cosmos. You cannot point a telescope at a void and expect to see much, because by definition, there is not much there to see. But there is something there. In fact, there are several things, and understanding them has turned the study of voids from a niche interest into one of the most active areas in cosmology. The first thing inside a void is dark matter, or more precisely, a much smaller than average amount of dark matter. The cosmic web's filaments and clusters are dense with dark matter halos, the invisible scaffolding that holds the visible structure together. Voids have very little of it by comparison, but they are not entirely empty of it either. Computer simulations reveal a faint skeletal structure inside voids, dim threads of dark matter, and a scattering of dwarf galaxies, far too faint to show up in most surveys, but present nonetheless. These ghost structures inside the voids trace what the web might have looked like in its earliest stages, before gravity had swept most of the material out to the edges. The second thing that voids contain, besides the Boötes tube of galaxies, is a specific class of galaxies that have become an object of increasing study: void galaxies. These are the rare, isolated galaxies that happen to reside deep within voids, rather than along the filaments of the web. And they are measurably different from their counterparts in denser regions. Void galaxies tend to be bluer, which is the signature of ongoing star formation. They are still building stars at a higher rate than galaxies in clusters, which have largely exhausted or lost their star-forming gas through interactions with neighboring galaxies and the hot intracluster medium. Void galaxies are also more frequently spiral in shape, and their morphology is more undisturbed. They have not been subjected to the gravitational harassment and tidal stripping that cluster galaxies routinely experience. In this sense, void galaxies are more pristine objects, preserved in a state closer to what galaxies in general looked like in the early universe, simply because the void environment is quieter and less disruptive. Studying them gives astronomers a way to understand galaxy evolution that is not possible in the crowded environments of clusters. There is also an interesting demographic pattern at the boundaries of voids. At the walls, the thin sheets of galaxies that mark the edges of voids, matter tends to have specific properties. Galaxies in these wall structures are being gravitationally compressed from both sides, pressed by the expanding voids they abut. The dynamics of these compression zones are different from the dynamics of galaxies deeper in filaments. The walls of voids, it turns out, are not just the borders of nothing. They are active regions of their own, shaped by the squeeze between the expanding emptiness on one side and the denser web on the other. The third thing inside a void, and the most consequential, is radiation. The cosmic microwave background, the faint afterglow of the Big Bang, the thermal radiation that has been traveling through space since the universe was 380,000 years old, fills all of space uniformly, including the deepest voids. No matter where you go in the universe, the CMB permeates the space around you. By the time it reaches us today, it has been stretched by the expansion of the universe to microwave wavelengths and carries almost no usable energy. But it is there, in every cubic centimeter, including the most barren volumes of the Boötes void. The fourth thing, and the one that ties everything together, is dark energy. And understanding what dark energy is doing inside the voids requires a small detour into what dark energy actually is, or at least into the best current understanding of a phenomenon that remains one of the great mysteries in all of physics. The something in the nothing. In quantum field theory, which is the framework that describes the behavior of fundamental particles, the vacuum is not truly empty. Every kind of particle corresponds to a field, a mathematical object that extends through all of space. And those fields are never at absolute zero energy. Even in a state of perfect vacuum, even with no particles present, the fields still exist and still carry a minimum amount of energy, called the zero-point energy or vacuum energy. This is not a hypothetical or a theoretical convenience. It is a real, measurable effect. The Casimir effect, for instance, is a phenomenon in which two uncharged metal plates placed very close together in a vacuum experience a slight attractive force caused by the quantum vacuum energy being slightly different between the plates than outside them. This has been measured in laboratories to high precision. The vacuum of space is not nothing. It carries energy by virtue of the quantum fields that permeate it. The energy of the quantum vacuum is believed to be the source of dark energy, or at minimum is believed to contribute to it. Dark energy is the name given to whatever is causing the expansion of the universe to accelerate, the force that is pushing galaxies apart at an ever-increasing rate. We know dark energy exists because the evidence for the universe's accelerating expansion is overwhelming, confirmed by multiple independent lines of evidence, including the behavior of distant supernovae, the structure of the cosmic microwave background, and the large-scale pattern of galaxy distribution. We know that dark energy currently accounts for roughly 68% of the total energy content of the observable universe. What we do not know, and what remains one of the deepest unsolved problems in physics, is precisely what it is and why it has the value it does. That second mystery, why dark energy has the value it has, is one of the most embarrassing discrepancies in all of physics. And it is worth dwelling on for a moment, because it gives a sense of how genuinely strange the situation is. When physicists try to calculate the energy of the quantum vacuum using the equations of quantum field theory, they get an answer that is enormously larger than the value astronomers actually measure. Not slightly larger, larger by something like 120 orders of magnitude, meaning a 1 followed by 120 zeros. This is the largest known discrepancy between a theoretical prediction and a measured value in all of science. It has been called the worst prediction in the history of physics. Something is clearly wrong, either in how we calculate the vacuum energy, or in the assumption that vacuum energy is the entire story of dark energy, or in both. The most commonly invoked explanations involve some kind of cancellation mechanism, a way in which contributions from different quantum fields partially cancel each other out, leaving a tiny residue that happens to match the observed value. But no one has ever produced a compelling theoretical account of why the cancellation should be so precise, leaving just the right amount of residual energy to match the cosmological constant that fits the data. This is an open wound in theoretical physics, and the voids, as the places where dark energy is most exposed, are the places where we can study it most directly. Here is the important thing for the voids. In dense regions of the universe, inside galaxies, inside clusters, inside the filaments of the web, dark energy is present, but it is completely dominated by the matter and radiation around it. Gravity, electromagnetic forces, the physics of stars and gas clouds, all of these overwhelm the effect of dark energy on scales smaller than tens of millions of light years. If dark energy suddenly vanished from our galaxy tomorrow, the Milky Way would continue to function in essentially the same way. Stars would follow the same paths. Planets would remain in their orbits. The daily experience of every form of matter in a dense region would be indistinguishable from what it is today. The voids are different. In the voids, there is almost no matter, almost no radiation beyond the CMB, almost no gravity to speak of at local scales. And in those conditions, dark energy, the energy of the vacuum itself, becomes the dominant presence. If you placed yourself at the center of a cosmic void, what surrounds you is not emptiness in any conventional sense. What surrounds you is dark energy, the energy of quantum fields vibrating through the fabric of space, operating without competition, without the suppression of dense matter. The voids are the places where dark energy is not just present, but powerful. They are the regions where it gets to do its work unimpeded. And what it is doing there has profound implications for the future of the universe. The void that grows. The most counterintuitive thing about cosmic voids is that they are not static. They are not simply regions where matter is scarce, waiting for structure to eventually form. They are growing. They have been growing since they first formed, and they are growing still, and the rate at which they grow is accelerating. As dark energy drives the expansion of space throughout the universe, its effect is not uniform. In dense regions such as galaxy clusters, filaments, the populated areas of the web, gravity is strong enough to resist the expansion locally. Those regions do not expand. The Milky Way is not getting larger. The distance from Earth to the Andromeda galaxy is not increasing. The two galaxies are actually approaching each other, pulled together by mutual gravity, and will eventually merge. On scales smaller than tens of millions of light years, gravity wins. But in the voids, gravity loses. There is not enough matter in a void to resist the outward push of dark energy, and so the voids expand. Space stretches within them, pushing their walls outward, pressing against the surrounding filaments and clusters. As a void expands, its edges push on the walls of galaxies that bound them, thinning those walls, disrupting them, and eventually causing them to break. When walls between adjacent voids become thin enough, they dissolve, and the voids merge. The product is a larger void, and then that larger void continues to grow, continues to push, continues to eat into the surrounding structure. This is a slow process by any human standard, operating over timescales of billions of years. But it is relentless, and the direction is one way. The voids expand, the structures around them thin. The walls and filaments of the cosmic web, which took billions of years to build through the patient accumulation of matter, are being gradually eroded from within. What we see when we map the cosmic web today, that intricate sprawling architecture of filaments and nodes and sheets, is a structure already in the process of being taken apart. Over the next 5 to 20 billion years, if current models hold, the cosmic web will continue to lose its fine structure to this process. Thin filaments will dissolve. Galaxy groups will be pulled apart by the expansion of the space between them. The voids will press against each other until the walls between them become so tenuous that they effectively cease to exist. What was once a complex web of structure will become a series of enormous, isolated islands of matter, remnant clusters and superclusters, gravitationally bound to themselves, but separated from all other matter by hundreds of millions of light years of near-perfect emptiness. And those islands will themselves continue to drift apart, not because gravity is weaker than it once was, but because the space between them is stretching faster than any gravitational force can bridge. It is worth being precise about what this looks like for specific structures. The Milky Way and Andromeda, along with the other galaxies of the local group, will eventually merge into a single massive elliptical galaxy, often called Milkomeda in speculative discussions. And this merged system will remain gravitationally bound indefinitely. The gravity of the merged local group is strong enough to resist the expansion of space on local scales, regardless of how dark energy behaves. The Milky Way is safe from dissolution in the direct sense. What it will lose over the next tens to hundreds of billions of years is everything else. All the other galaxy clusters, visible today as tiny smudges in telescope images, will recede beyond the cosmic horizon. The Virgo cluster, the Coma cluster, the thousands of other clusters that today paint the sky in galaxy surveys, all of them will eventually cross the threshold of observability and vanish. What will remain for any observer sitting in the merged local group is a single gravitationally bound system surrounded by expanding emptiness. The voids are not waiting for structure to develop inside them. They are actively dissolving the structure that exists around them. And the engine driving that dissolution is the same engine that built the voids in the first place. Dark energy, working through the expansion of space, most powerfully in the regions where matter is too scarce to slow it down. The great nothing next door. Here is something strange. The void in which the universe currently seems to be doing the most dramatic work is not Boötes 700 million light-years away. it might be much closer. It might, in fact, be the void that the Milky Way itself is sitting in. In 2013, a team of astronomers led by Ryan Keenan, Amy Barger, and Lennox Cowie published findings suggesting that our galaxy resides within a large underdense region, a region where the density of matter is meaningfully below the cosmic average. This region, now known as the KBC void after its discoverers, appears to extend roughly 1 billion light-years in all directions from the Milky Way. It is not empty in the way the Bootes void is empty. It contains many thousands of galaxies, including the entirety of the local group and the larger Laniakea supercluster. But the overall density of matter within it is estimated to be around 20% below the cosmic mean, which, on cosmological scales, is a substantial underdensity. The existence of the KBC void is still debated among astronomers. Not everyone agrees on its extent or its depth. But if it is real, and the current measurements are roughly correct, it has an implication that cosmologists have been wrestling with for years, because it might be connected to one of the most significant unsolved problems in contemporary physics. The problem is called the Hubble tension. The Hubble constant is the rate at which the universe is expanding, measured in kilometers per second per megaparsec of distance. There are two main ways to measure it. One uses observations of the distant universe, particularly the pattern of the cosmic microwave background and the spacing of large-scale structures, and yields a value of roughly 67 to 68 kilometers per second per megaparsec. The other uses the local universe, measurements of distances to nearby galaxies using Cepheid variable stars and Type Ia supernovae, and consistently yields a value of roughly 72 to 74 kilometers per second per megaparsec. Both methods have been refined over years of work. Both have been checked for systematic errors many times, and both remain stubbornly inconsistent with each other. The discrepancy, now measured at several times the statistical margin of error, suggests that something in our understanding of the cosmos is incomplete. One proposed explanation is that we happen to live in a void. Matter inside an underdense region experiences a net outward gravitational pull from the denser region surrounding it, as if the void were a basin and the matter at its edges were being drawn up toward the walls. This creates a local excess of outward velocity on top of the general cosmic expansion, inflating the locally measured expansion rate compared to what would be measured from outside the void or from averaging across the universe as a whole. In other words, if the Milky Way sits inside a large void, our local measurements of the expansion rate could be systematically biased upward, producing a higher apparent Hubble constant than the true global value. Researcher Indranil Banik and colleagues at the University of St. Andrews have argued that the KBC void, if accurately characterized, could account for an increase of roughly 11% in locally measured expansion rates, enough to explain most or all of the Hubble tension. This is not a settled question. Critics have pointed to difficulties reconciling the size and depth of the proposed void with the predictions of standard cosmological models, which do not easily produce voids as large and deep as the KBC appears to be. The debate continues, and the tension has not been resolved. But the possibility that the voids, the great empty expanses of the cosmos, might be directly shaping one of the most important measurements in cosmology is a striking illustration of how consequential these supposedly empty regions have turned out to be. The terrifying part. The dissolution of the cosmic web is only half the problem. The other half is subtler, and in some ways more disturbing. As the web dissolves, the universe is simultaneously erasing the evidence that it ever existed. Here is how that works. The observable universe, everything we can in principle detect, is defined by the distance light has had time to travel since the Big Bang. But that boundary is not fixed. Because the expansion of space is accelerating, Galaxies beyond a certain distance are receding faster than light can cross the gap between us and them. The light they emit now will never reach us. They have crossed what physicists call the cosmic horizon, and for all observational purposes, they are gone. Not destroyed, still there, still burning, but permanently beyond the reach of any signal. Right now, the observable universe contains approximately 2 trillion galaxies. That number is shrinking. Every year, more galaxies cross the horizon than enter it. The observable universe is, in terms of its galaxy count, slowly contracting around us even as physical space continues to expand. Each galaxy that crosses the horizon takes its information, its redshift, its chemical composition, its position in the web, with it permanently. That information cannot be recovered by any telescope, however powerful, because there is no longer any light from those galaxies arriving here to be collected. Cosmologists have calculated that roughly 150 billion years from now, all galaxies beyond the local group will have passed beyond the horizon. The sky at that point will contain the stars of the merged Milky Way Andromeda system and nothing else at any practical resolution. The CMB will have been stretched by then to wavelengths so long, radio waves millions of times longer than the universe is old, that detecting it would require an antenna the size of the solar system. It will be functionally undetectable. What this means is that the entire evidentiary basis for modern cosmology will have vanished. In the early 20th century, the most important debate in astronomy was whether the spiral nebulae visible through telescopes were small clouds inside the Milky Way, or vast stellar systems at enormous distances, other galaxies in their own right. Edwin Hubble resolved that debate in the 1920s by measuring the distance to Andromeda using Cepheid variable stars, finding it vastly farther than any Milky Way structure. From there, the redshifts of distant galaxies revealed cosmic expansion, which led to the Big Bang theory, which led to everything we now understand about the universe's origin and structure. Every step in that chain of discovery depended on having nearby galaxies close enough to study in detail. In 150 billion years, no such galaxies will exist within observational reach. A civilization arising then would find themselves in a cosmos that appears, by every measurement available to them, to consist of a single gravitationally bound stellar system surrounded by infinite empty darkness. The expansion of space would be undetectable, no distant galaxies to show redshifts. The Big Bang would be unverifiable, the CMB gone. The cosmic web would leave no trace. The entire framework of modern cosmology would be not wrong, but permanently unrecoverable. The terrifying part, in other words, is not that the universe will become empty. It is that it will become unknowable. The voids are not just consuming the web, they are consuming the record of the web. The expansion of space is erasing its own history, and the window during which that history is legible is one we currently occupy and will not occupy for much longer on cosmic timescales. Voids as laboratories. For most of the history of modern astronomy, cosmic voids were treated as the spaces you passed through on the way to something more interesting. The galaxies were the objects of study. The filaments and clusters were where the action was. The voids were just what filled in the map between them. That has changed substantially in recent years, and the shift has been driven by the recognition that voids are not passive containers for dark energy. They are dynamic objects with measurable properties, and those properties encode an enormous amount of information about the fundamental physics of the cosmos. Consider what makes a void useful as a scientific tool. In dense regions, galaxy clusters and filaments, the physics is complicated. Galaxies are colliding, gas is being heated and compressed, black holes are ejecting material at high energies, dark matter is clumping into complex halos. All of these processes interact with each other, and teasing apart the effects of any single variable is difficult. The voids, by contrast, are quiet. The matter inside them is sparse and relatively undisturbed. The dynamics are simple enough to model precisely. One of the clearest demonstrations that voids leave measurable physical signatures came from the study of the cosmic microwave background. When photons from the CMB travel toward us, they pass through the large-scale structure of the universe, through filaments, through clusters, through voids. As a photon falls into a dense region, it gains energy from the gravitational well. As it climbs back out, it loses that energy again. In a static universe, these effects would cancel perfectly. But in an expanding universe, the gravitational well is slightly shallower when the photon climbs out than it was when it fell in, because the expansion has stretched the well during transit. This means photons gain a tiny net boost of energy passing through dense regions, and lose a tiny net amount of energy passing through underdense regions. The effect is called the late-time Sachs-Wolf effect, and it leaves a measurable imprint. Slightly colder patches on the CMB map correspond to the locations of cosmic voids. The WIMAP satellite and its successor Planck have mapped the CMB in fine detail, and researchers studying those maps have found cold spots corresponding to large voids in the distribution of galaxies. The statistical correlation is real and measured, and it provides direct physical evidence that dark energy is responsible for the expansion. Because the Sachs-Wolf effect that produces it only works if the universe is dominated by dark energy. In a matter-only universe expanding without dark energy, the gravitational wells would be static, and the effect would cancel. The cold imprints of voids on the CMB are, in this sense, a signature written by dark energy itself, readable in the oldest light in the universe. There is also, notably, an unusually large cold spot in the CMB in the direction of the constellation Eridanus, detected originally by the WMAP satellite. Some cosmologists have proposed that this cold spot could be explained by a supervoid along that line of sight, an enormous underdense region that, via the Sachs-Wolf mechanism, would produce exactly this kind of cold imprint. The search for a corresponding void has found some evidence of an underdense region in that direction, though whether it is large enough and deep enough to fully account for the cold spot remains debated. If the Eridanus supervoid is ultimately confirmed as the explanation, it would represent the largest known void in the universe, potentially 1.8 billion light-years across, and would be the first direct imaging of a specific void signature on the CMB. This is what makes voids useful as a scientific tool. They are extraordinarily sensitive probes of dark energy. Because the voids expand under dark energy's influence, and because they have very little competing matter to complicate the picture, the rate at which voids grow, and how that rate has changed over the history of the universe, directly reflects the behavior of dark energy over time. Measuring the size distribution of voids in the early universe and comparing it to their size distribution today amounts to watching dark energy work in its most favorable environment, without the confounding influence of dense matter. Future surveys, including data from the Euclid Space Telescope launched in 2023, are expected to map voids across vast volumes of the universe precisely for this purpose. Voids are also sensitive probes of neutrinos, the lightweight subatomic particles that are among the most abundant in the universe, but interact so weakly with ordinary matter that they are extraordinarily difficult to study directly. Neutrinos have mass. Exactly how much mass is one of the genuinely open questions in particle physics, and that mass affects their behavior in the early universe. Heavy neutrinos would have moved more slowly after the Big Bang, clustering with ordinary matter and filling voids from the inside. Light neutrinos would have streamed freely through voids, escaping from them and leaving them emptier. The statistics of void sizes, how many there are, how large they tend to be, how empty their interiors are sensitive to neutrino mass in ways that future void surveys are designed to exploit. Probing particle physics through the emptiest regions of space is not intuitive, but it is becoming a genuine experimental strategy. And voids have already confirmed something important about gravity. Einstein's general theory of relativity predicts how matter curves space-time, and how that curvature affects the motion of everything, including light. When light from a distant galaxy travels through a cosmic void, it passes through a region of very different space-time curvature than it would experience passing through a cluster. The way that light is bent and the statistical pattern of its bending across many such encounters can be compared to the predictions of general relativity on the largest scales it has ever been tested. The results, so far, suggest that general relativity holds even at these extreme scales, which is itself important information, ruling out some alternative theories of gravity that might otherwise seem like plausible explanations for dark energy. There is one more property of voids that researchers have begun to exploit: their shape. In a universe governed by standard general relativity with a cosmological constant, voids have a specific statistical distribution of shapes, some more spherical, some more elongated, determined by the interplay between dark energy expansion and the gravitational pull of surrounding matter. In modified gravity theories, such as the FR models that alter how the gravitational force behaves on large scales, the internal dynamics of voids are different. Matter inside a void responds to gravity differently under these theories, which changes how quickly the void evacuates itself, and therefore distorts its average shape. By measuring the shapes of thousands of voids in a large galaxy survey and comparing the statistical distribution to predictions, researchers can test whether standard gravity or a modified version is at work, a test that is largely impossible to perform in dense environments where the physics is too complicated to isolate. Void shapes are, in this sense, a clean window onto the law of gravity itself, written in empty space. What was once the least interesting part of the universe map has become a precision instrument. How the void shapes what lives in it. The cosmic web does not just determine where galaxies are, it determines what kind of galaxies they are. And the contrast between galaxies in the dense filaments of the web and galaxies stranded in the voids is one of the clearest demonstrations that environment, not just initial conditions, drives the evolution of structure. In the dense nodes and filaments of the web, places like the Virgo cluster, the Coma cluster, the intersections where superclusters concentrate, galaxies are almost exclusively elliptical. Elliptical galaxies are old systems, smooth and featureless, containing mostly ancient red stars and very little gas. They form very few new stars, and in many cases have not formed new stars for billions of years. The reason is the environment. In crowded clusters, galaxies interact constantly. Tidal forces strip gas from their disks. High-speed collisions heat and disperse star-forming material, and the hot intra-cluster medium exerts a ram pressure that sweeps the cold gas out of a galaxy like wind blows leaves off a moving car. This process is called ram pressure stripping, and it is one of the primary mechanisms by which the web kills star formation in its densest nodes. The walls and filaments also play a subtler role. As matter flows along filaments toward cluster nodes, it heats up through a process called shock heating. The gas that arrives at a dense node has been accelerated by gravity and thermalized to temperatures of tens of millions of degrees, hot enough that it can no longer collapse to form stars. Instead, It sits in a diffuse halo of hot plasma called the intracluster medium, effectively frozen out of the star formation process. The energy that built the web's most massive structures is the same energy that shut down star formation inside them. Void galaxies face the opposite situation. They are isolated from the mechanisms that strip and heat gas. Their interstellar medium is undisturbed. Cold gas accumulates over time, and the void's galaxies continue forming stars at rates that reflect the steady, unhurried accretion of material from the near-empty space around them. This is why void galaxies are systematically bluer than their cluster counterparts. Blue is the color of hot young stars, which are only present when star formation is actively ongoing. It is also why they are more likely to be spirals. Spiral structure requires a settled, rotating disk of gas, exactly the kind of structure that gets disrupted in the crowded environment of a cluster. The relative peace of a void preserves the spiral form. Between the voids and the cluster cores lies a transitional zone, the walls and filaments themselves, where intermediate-type galaxies called lenticulars are common. Lenticular galaxies have disk structure like spirals, but lack the spiral arms and have mostly exhausted their gas, placing them somewhere between a spiral and an elliptical in the morphological sequence. Their prevalence at the boundaries of voids and clusters makes them something like a record of a transition in progress. Galaxies that have entered a denser environment, begun to have their gas stripped, but have not yet been fully disrupted into featureless ellipticals. In this sense, the morphology of a galaxy is partly a timestamp, a record of when and how deeply it has been drawn into the web's denser regions. The distribution of galaxy types across the universe is not random, but is a map of the web itself, written in the shapes of the galaxies it contains. The most spectacular galaxies, the massive, luminous ellipticals at the centers of great clusters, are in one sense the most evolved, the end products of billions of years of mergers and interactions. But they are also, in terms of ongoing activity, effectively dead. The scrappy spirals out in the voids, unremarkable individually, are still building themselves, still converting gas into stars, still doing the thing that galaxies primarily exist to do. The quietest, emptiest regions of the universe are the ones where the process of galaxy formation has the longest and most uninterrupted run. This has implications for life. Planet formation requires heavy elements, carbon, oxygen, silicon, iron, that were manufactured in stellar interiors over generations of star birth and death. Regions where star formation was quenched early, as in the dense cluster cores, have older stellar populations with less of this chemical enrichment in their younger stars. The conditions for rocky planets and complex chemistry have had less time to develop. The voids, precisely because their galaxies kept forming stars for longer, may harbor a higher proportion of chemically enriched stellar environments suitable for planetary systems. It is one of the stranger ironies of cosmic structure. The most desolate regions in the universe on large scales may, on the scale of individual star systems, be among the better candidates for the conditions life requires. After the web, what comes after the void's win is a sequence of events that cosmologists have mapped in considerable detail, unfolding over timescales so large that the current age of the universe would appear as a rounding error. The stars inside the surviving galaxy clusters burn through their fuel over an enormous range of timescales, from millions of years for the most massive to trillions of years for the smallest red dwarfs. The Sun will exhaust its hydrogen in roughly 5 billion years, expand into a red giant and collapse into a white dwarf. The smallest red dwarf stars will continue burning for roughly 10 trillion years. about 1,000 times the current age of the universe. After 10 trillion to 100 trillion years, all star formation has ceased, all stars have expired, and what remains of the galaxy consists of white dwarfs, slowly cooling. Neutron stars, black holes, and cold brown dwarfs that never manage to ignite. Cosmologists call this the degenerate era, dark, cold, and extremely quiet. A universe lit only by the faint infrared glow of cooling stellar remnants. During this era, the galaxies themselves, or rather the gravitationally bound collections of dead stellar remnants that were once galaxies, continue to evolve through a process called dynamical relaxation. Stars, or in this case their remnants, interact gravitationally with each other over long periods of time, gradually redistributing energy. Some objects are accelerated through these interactions and gain enough velocity to escape the galaxy entirely. Others lose energy and sink toward the center. The net effect, playing out over timescales of roughly 10 to the power of 19 to 10 to the power of 20 years, is that galaxies slowly evaporate. The majority of their stellar remnants are ejected into the intergalactic void, while the minority that have sunk toward the center accumulate around the central supermassive black hole. By the time all ordinary stars have been dead for many trillions of years, the once grand galaxies will have dispersed into a sparse population of cold objects drifting through intergalactic space, with a black hole at the center of each former galaxy, slowly consuming the last material within its gravitational reach. But even then, matter is not finished changing. Individual atoms are, under the standard model of particle physics, theoretically unstable over astronomical timescales. Proton decay, a process predicted by many grand unified theories, though not yet observed experimentally, would gradually disassemble atomic nuclei over timescales somewhere between 10 to the power of 34 and 10 to the power of 40 years. If proton decay occurs on any of these timescales, then by around 10 to the power of 40 years after the Big Bang, all ordinary matter will have dissolved into radiation and leptons. The white dwarfs, the neutron stars, the cold planets, all of it will have evaporated. The only remaining structures will be black holes. Black holes are themselves not permanent. Stephen Hawking showed in 1974 that black holes slowly radiate energy, a quantum mechanical process now called Hawking radiation, and will eventually evaporate completely. The time required depends on mass. A stellar mass black hole would take roughly 10 to the power of 67 years to evaporate. The supermassive black holes at the centers of galaxies, which can contain billions of solar masses, will take up to 10 to the power of 100 years. After that, nothing remains but a diffuse gas of photons and leptons expanding through an increasingly cold, increasingly empty universe. This endpoint, often called the heat death of the universe, is a state of maximum entropy, minimum structure, and effectively zero available energy. It is the ultimate expression of the emptiness that the voids have been working toward since the first billion years of cosmic history. None of this is speculation in the dramatic sense. It follows directly from established physics, applied forward in time. The voids are not just large empty spaces in the universe as it exists today. They are the leading edge of a process that, run to completion, produces a universe that is not just mostly empty, but entirely empty of everything except the fading afterglow of the last evaporating black hole. If dark energy is not what we think, everything so far has assumed that dark energy behaves as a cosmological constant, a fixed, unchanging property of the vacuum with the same energy density at every point in space and at every moment in time. That assumption underlies the standard cosmological model called lambda CDM, and it fits the available data extremely well. But fitting the available data is not the same as being correct, and there are early signs that the cosmological constant might be more complicated than it appears. In 2024, the Dark Energy Spectroscopic Instrument released its first major set of results from a survey of over 6 million galaxies, representing the most precise three-dimensional map of the large-scale structure of the universe ever produced at that point. The DESI team found that when they fitted their data to models of dark energy, the best fit was not a constant value, but a value that appears to change over time, growing stronger in the recent past and potentially weaker in the earlier universe. The statistical significance of the deviation from a constant was not overwhelming. Physicists describe it as a roughly 2 to 3 sigma hint rather than a definitive discovery, but it was present across multiple independent analyses, and it has not gone away in subsequent checks. To understand what variable dark energy would mean, it helps to know how physicists parameterize it. The standard approach uses two numbers, called W0 and WA, which together describe how the dark energy equation of state evolves with the expansion of the universe. A cosmological constant has W0 equal to -1 and WEA equal to 0. It does not change. What DESI found was that the best fit values of these parameters sit away from that point, in a direction suggesting dark energy was weaker in the early universe and has been strengthening over time. If this is correct, the rate of void growth in the early universe would have been slower than the cosmological constant predicts, while the rate today and into the future would be faster. The voids we observe today would be slightly smaller than they would be under a true cosmological constant, which could also potentially address some of the tension between theoretical predictions of void sizes and what surveys actually find. If dark energy varies with time, the implications for everything would need to be revised. A dark energy that grows stronger over time would cause the expansion of the universe to accelerate faster than the cosmological constant predicts. In the most extreme version of this, a scenario called phantom dark energy, in which the energy density increases without limit as the universe expands. The result would not be the gentle long-term dissolution of the cosmic web described earlier. It would be something far more abrupt. In a phantom dark energy universe, the expansion would eventually become so rapid that it overcomes not just the gravity holding galaxy clusters together, but the gravity holding individual galaxies together. Then the gravity holding solar systems together. Then the electromagnetic forces holding atoms together. In the final moments before the endpoint, space would be expanding so violently on every scale that molecules would be torn apart, then atoms, then atomic nuclei. This scenario has a name: the Big Rip. Calculations suggest it would occur roughly 20 billion years from now, if current hints of variable dark energy reflect the true behavior of the universe. The Big Rip is not considered the most likely outcome. The cosmological constant model still fits all available data within its uncertainty range, and the DESI deviations could yet be explained by systematic errors in the survey. But the fact that the question is genuinely open, that measurements as of the mid-2020s cannot rule out a future in which the fabric of space tears apart on subatomic scales, is a reminder of how incompletely we understand the force that dominates 68% of the universe's energy budget. The voids exist because of dark energy. What dark energy actually is and how it will behave in the future is not settled. The most consequential force in the cosmos remains, at its core, mysterious. The window. There is a concept in astronomy called the cosmic coincidence problem. It is related to the cosmological constant problem, but distinct from it. And it states that dark energy and matter currently contribute roughly comparable amounts to the total energy content of the universe. Dark energy accounts for about 68%. Matter, including both ordinary and dark matter, accounts for most of the rest. These proportions are close enough that neither completely dominates the other. We are in a period where both are significant players. This seems unremarkable until you consider the timeline. For the first several billion years of the universe's history, matter dominated almost entirely. Dark energy was present, but negligible. Too small a fraction of the total energy budget to have any meaningful effect on structure formation. During that era, gravity ran the show, building the cosmic web, forming galaxies, igniting stars. Then, roughly 5 to 6 billion years ago, the proportions shifted. The universe had expanded enough that the density of matter had thinned to the point where dark energy, whose density does not dilute with expansion, began to catch up and overtake it. The expansion began to accelerate. The voids began growing in earnest. In the far future, matter will be even more diluted. Dark energy will account for an ever larger fraction of the total energy. The era of matter's significance, the era we are currently in, is a window, and it is already past its midpoint. We live in the brief period between matter's dominance and dark energy's complete victory, the only period in which stars burn and galaxies persist, and the cosmic web maintains some semblance of its structure. The physicist Steven Weinberg pointed out in 1987 that if the cosmological constant were even a few times larger than its actual value, the universe's expansion would have accelerated before structures could form. Galaxies, stars, and planets require time. They need billions of years of gravitational collapse and chemical enrichment. A cosmological constant, only modestly larger than observed, would have begun accelerating the expansion before the first large galaxies assembled, freezing the universe into a sparse scatter of small, poorly enriched structures. The window between the Big Bang and the onset of accelerating expansion would have been too narrow for complexity to arise. If the cosmological constant were smaller, closer to zero, the window would be wider and structure would have more time to build. But at zero, dark energy disappears entirely, the expansion decelerates, and the universe eventually recollapses in what physicists call the Big Crunch. Not a slow dissolution, but a reversal, everything falling back together in a mirror of the Big Bang. The actual value produces exactly the right behavior. Enough time for structure, enough dark energy to eventually accelerate and prevent the collapse, and enough of a gap between those two phases that planets form and chemistry runs. And apparently things wonder about it. The narrowness of that window, and the fact that we occupy it, is either a remarkable coincidence, a product of anthropic selection, or evidence of physics we have not yet identified. The question of why we happen to exist during this window, rather than in the billions of years before it opened, when no planets existed, or in the trillions of years after it closes, when no stars remain, does not have a consensus scientific answer. It connects to the cosmological constant problem, to questions about whether the universe is the only one or one of many, and to the still unsettled question of why the constants of physics have the specific values they do. These are not fringe speculations. They are the live edges of physics as it is actually practiced, questions that appear in the most serious journals and occupy some of the best minds in the field without resolution. What is unambiguous is the direction the universe is moving. The voids are growing. The web is thinning. The observable universe is contracting in the only sense that matters. The number of things it contains that we can reach, measure, or know anything about is declining. We are not at risk of running out of time to answer these questions in any individual human lifetime. But on the scale on which the universe operates, the window is not infinite, and it is not getting wider. The fact that all of this, the scale of the emptiness, the mechanics of the voids, the trajectory of the cosmos, is knowable at all, from one small planet in one ordinary galaxy, is genuinely strange. It does not have to be. There is no physical law requiring that the universe be the kind of place that produces entities capable of asking questions about it. That it does, and that we are those entities, and that we happen to exist at the precise era when the evidence is still available to be read. That is, by any reasonable measure, remarkable. Whether it matters is a different question, but it is, at minimum, worth noticing. What we are, this planet, these atoms, this moment of understanding, is a temporary exception to an overwhelming rule. That is not a reason for despair. It might be the best possible reason to pay attention. If this is the kind of thing that interests you, subscribe. There is more to cover, and it only gets stranger from here.